Okay, we are moving on to the last section of the chapter, which is a mesh hall diagram. So whenever there's a construction of roads, highways, railway tracks, canal, a vast amount of earthwork is involved. You'll see lorries, you see vehicle carrying, ferrying material, hauling material from one place to another, either along the side where the material will be dumped to fill, the area needs to be filled, or there will be also instances where the material cut or excavated will not be used for the site. In the site, it will be dumped outside the site. And in engineering term, we call that a waste. Okay, so a waste simply means material that been excavated and not used in the construction at the site. And at the same time, if we have a condition whereby area need to be filled, but there's nowhere, no material to be found nearby, not from the construction site, that means we could take it from outside. We've got to import the material from outside, and we term that as borrow. Okay, so borrow, meaning material that we don't require, material that we need but not available at that site. And waste is material that unsuitable to be used will be dumped somewhere else outside the site area. So the movement of transportation material or the movement of earth or soil is costly. So we need some kind of planning. We need some kind of program whereby to manage the movement of the soil. Movement in terms of the haulage, where the soil be transported to. If you could imagine, I think you can appreciate by now that when we talk about road construction or highway construction, we're talking about long distances. We're talking about, tens and 20s of kilometers away. So obviously, if you excavate one area, so you got to decide what to do with that, the material that been excavated. Either you want to transport it along the alignment to another spot to be filled, or you decide that that material is too far away to be transported, and you decide to treat it as a waste. So all in all, in a nutshell, you need some kind of planning. There should be a strategy and how you should manage the movement or the transportation of the soil. And this is, you can do that with the help of what we call a mesh hall diagrams. A mesh hall diagrams. Sometimes they're called, in some textbooks, they're referred to as mesh diagrams. They're both the same thing. It's just a matter of a different terminology. Okay, I think the next slide shows what a mesh hall diagram is. It's a diagram, okay, it's basically a graph of what? Of a cumulative volume on the y-axis against the change on the x-axis. Okay, so if you look at this diagram, the y-axis there is basically the cumulative volume. Okay, and the x-axis is basically the change. So So the figure up there, the figure up here is the profile, is the longitudinal section, whereas this is the mess hall. Okay, so this is the mess hall. So this is basically the long. Excuse me. Let me just get back to where we were previous. Okay, so this is the long section. Okay. Okay, if you look at that that part there, okay, this part here. Okay, we're going to start from A. If we move towards B, we'll be excavating. Okay, when we excavate, the volume will increase, and the volume of excavation will increase till we get to B, whereby it's going to be a fill, so the volume that we obtain will decrease. So that's the reason why up to that point the graph rises, the curve rises. So that's to show it's a cut. So when the graph goes down up to that point there, if I just produce this up, that's to show that area is fill. So this is a fill area, okay, as shown on the figure up there. Similarly, on the next section. So if you can somehow use this figure to manage where the cut material to be transported to and how far, so that will be some kind of planning on your part as far as the transportation of soil is concerned. We'll do a little exercise on that later. But before we go on, let's look at some terminology that we'll be using when we're dealing with a mesh haul diagram. First and foremost is haul. Okay, haul meaning carry or transport. So it's basically the cost of earth moving, and it's given by a very simple formula of volume times distance. Volume is meter, meter cube, distance is meter. So the unit is meter cube meter, and sometimes termed as station meters. So station meter simply refers to meter cube meter. Then we've got the average haul distance. Okay, if I can just go back to the previous one just to explain what I mean by average haul distance. Okay, let's say we excavated that area there. Okay, and we decide that, okay, for argument's sake, let's say the area or that volume that we excavated can be filled onto that area. Okay, I'm just making this up. It might not be true, but let's say, okay, wherever we excavate there will be transported, will be filled into the area. So now when we move, we might be excavating that part, and doesn't necessarily we will dump it there. We might dump it that part at the far end. Then we do that one, the next area. Then we will decide to do it there, or perhaps we do it there, okay, the beginning of the area, and decide to put next to the one that we just dumped. So the distance varies from point to point. So for that reason, what we'll do, we'll take the average distance, which simply means that center to that center. So that's the average distance, okay, the average haul distance. So that's what we have here, okay. So average haul distance is basically the distance from the center of gravity of excavation to the center of gravity of the tip. Simply the center of the excavation to the center of the tip or the fill area, okay, or probably call it the fill area, okay. Alright, and freehold distance is a distance whereby stipulated in the contract, okay, and it says within that distance, if you transport soil within that distance, they won't charge you for hauling. So there's no hauling charges. You only have to pay for excavation charges. So it might be a few hundred meters, depending on what the contract says. So that's freehold distance. Then conversely, we'll have overhaul distance, which simply means whatever the balance, or whatever the surplus of the distance that we travel, minus the freehold, that will be the overhaul distance, or the distance of which materials or soils that need to be transported in excess of the freehold distance. Overhaul distance, if you want to put it in equation form, is simply be average haul distance minus freehold distance. Then we have waste. Okay, we talked about it just now. Waste material that need to be exported from a section of the site due to surplus or unsuitability. So not all soil that we excavate suitable to be used. Might not be suitable, so we might just have to dump it somewhere else as waste or surplus. Now, borrow simply means, again, material that we need to be imported into the site because we don't have enough along or within the site area. So that's waste and borrow. Okay, next, balancing line, which is a very important concept in Mushairry diagram. Balancing line here, just if you want to put it in words, it simply means a line that intersects the Mushairry curve at 2 points or more. Okay, and what is the significance of the balancing line? It says, okay, the earthwork between these 2 points are balanced. It means volume of cut or volume of excavation will be equal to volume of fill. Now, horizontal line is any horizontal line. I think I should probably add to that, is that any horizontal line which is parallel to the x-axis. Okay. Okay. So the x-axis itself. Okay. X-axis itself is a balancing line. Okay, it's a balancing line. So, if I were to draw a balancing line, let's say there, which is parallel to x-axis, what does that signify? Okay, so if I project that line to that point there, and project that line where the intersect is to that point there. So the balancing line simply is tell me whatever I excavate there will be enough for me to fill that area. Okay, so that's what balancing line is. So what does it? What? That's what it means. Okay. Now, looking back at the, if I just erase that, okay, erase that, and let's assume, or let's say that I'm going to take the x-axis of the balancing line. So that means if I project that point onto the long section, and the other one will be here, okay, long section. So that tells me all this will be enough to fill everything in there up to that point. And if you look at the other curve, there's the second part of the curve here. So that also tells me that, because that's a balancing line, because it cuts at 2 points, 1 point there, another point there. So if I project that up onto the cross section, on the long section, so in this case, I'll probably use a different color. I'll use dark blue now. So whatever I cut there, I can fill it there. Okay, so that leaves us with a part of the site that we excavated, which is that part there, which will not be used in the construction, because we have filled the area that need to be filled. So that is what we term as waste. Okay, so that's what we mean by waste, construction waste. Okay, so let's look at a different scenario now. Let me just delete all this. Okay, and delete that one too. Okay. Okay. Let's say for some reason or another, the soil from there to there is not suitable. Maybe it's silty, clayey, the strength is not good. Okay, so sandy, not suitable to be used to be filled. So we don't need that material. So we cannot use that material. So in that case, okay, if I bring that down, if I were to draw a horizontal line which represents a balancing line, so if I project that up to the long section, so I know that whatever I excavate there will be used all together there. Okay, then if I draw another line there, from there to there, project it up here, okay, project it up onto the long section. Okay, again, that tells me that area can be filled with that material. Okay, so in this case, what happens here, we've got that part is going to be waste. Okay, and that part is also waste. Right, and we have one area that will be empty, need soil. So this is where we will be borrowing. So that area needs borrow. Okay, so there might be cases like this, okay, where you have no choice because of certain restriction or certain constraints, unsuitability of soil, and similar conditions. You cannot use the soil, you cannot use the method that you excavated. To dump it somewhere as waste, then you have to borrow in order to come up with the proposed level of your field area. Okay, so that's a terminology I think that you should know before we can proceed with the analysis of the diagram itself. Okay, let's do one example here. I've got a table on the left of the screen, the table changed from 0, okay, right down to 700, so 700 meter stretch, okay, whereby it says we know that between 0 to 50 is a fill, 50 meter cube, 50 to 100 a fill of 70, 380, and so on till we get to change between 300 and 350 is a cut, okay, and it's a cut all the way down till we get to the last change, which is change 700. Okay, the question says, okay, you got to use that figure, got to plot the mass flow diagram by assuming a bulking factor of 10%. Okay, and you've learned that in soil mechanics. Bulking factor simply means that when you excavate soil, when you transport it, okay, the volume will exceed from what you excavated because of air voids. And because the soil was previously compacted, now the soil is loose, so there'll be voids. So the void will make up space. So in this case, let's assume that it takes 10% of the original volume. And the question also says that if the balancing line is at cumulative volume minus 200 meter cube, estimate the total cost of haul given the following rate: excavation 5 ringgit 20 per meter cube, and overhaul 6 ringgit 80 per station meter offer per meter cube meter. Okay. Okay, so what I have here is an Excel sheet, okay, of the problem, of the Mushairry exercise, and I put it down there. That's a chainage, that's a cut, that's a fill. A bulking factor or bulkage of 10%. So remember, a bulking or bulkage factor only applies to cut material, okay? So you don't apply any correction to the fill volume. So in this case, there's none there. So 10% of 109, so I've rounded up. I take round number here, just the integer. So 11, about 11, 10.9, so about 11. You don't have to be too accurate or too critical about it. So 16, 13, so 10% of each. And then I have the corrected volume there. Okay. So 0, minus 50, 70, and so forth. And the last column here. Okay, remember? Mushairry diagram, chainage versus cumulative volume. Okay, so you got to add up all the volume. Okay, 50, 120, 500, and so on to get to the last point, or the last chainage, which gives you 401. So we're going to use that chainage. We use that cumulative volume. We will use that to do the diagram or the plot. So I prepared a plot, or I've done it, which looks something like this. Okay, let me just take it down a bit. All right, so that's how the plot looks like. Chainage 0, okay, 50, 100, and so on. It goes down and then it goes up. All right, so area down meaning curve going down means cut. Curve going up means signify. Sorry, I made a mistake there. A curve going down signify a fill, whereas a curve going up means it's a cut. So there's a fill there, it's a cut there. All right, so let's read the question again. It says the balancing line is at volume, cumulative volume, negative 200. Okay, 200 meter cube. So we know that a balancing line should be parallel to the x-axis. So what you have to do now, I have prepared the lines, okay, just to make things, to expedite things. So you have to draw a line now, horizontal, and place it on the 200 meter cube line, just to show you that is a balancing line. Okay, now after that, once you've got that, you have to find out what is the whole volume. You want to find out what's the whole volume, the total volume that will be hauled, that will be transported. So it's given by simply the vertical line. If I just move it from there, the vertical line from the very top, for the very bottom part of the curve to the balancing, so to the balancing line. So that line represents the volume. Okay, so what is the volume? Okay, let's say that's the line. So that's the line. So I'm going to put it against this, so that I could tell what the volume is. So it looks to me like it's about 700, maybe 80 or 790. So do not be too critical with this. It's a graphical way of doing things. It's only an estimate. I think it's good enough just to scale it off the axis. Okay, but if you like, you can find out the scale and multiply the distance and whatnot. But I would say, I would just look at the line. I would say that's about 780-ish. Okay, so I probably just put in there now, whole volume will be about 780. Okay, now let's bring that back to this. Okay, so that is basically the whole volume. Okay. Now, the next thing to do, okay, is to find the freehold volume. Yeah, to find the freehold volume here. Okay, that volume there. But in order to find the freehold volume, we have to draw the freehold distance. Okay, so remember, freehold distance given was 200 meter. Okay. Okay. I think I've forgotten to mention in the question. Okay. But anyway, let's say freehold. I'm just going to type it somewhere here. Okay. Given where should I put it there? I put it there? Yeah. Okay. Given freehold distance is 200 meter. Okay. Okay. Let's say 200 meter. So I'm going to draw a line. I think this green line here. If I just put it against there, you can see it's about 200 meter long. It's about 200 meter long, between 3 to 400. So I'm going to take that line, I'm going to bring it down so that I hit the curve at 2 points like that. Okay, so that is how you draw the freehold distance in parallel, and it hits the curve at 2 points like that. Okay, let me just move this so that it's not in the way. Okay, let's put it up there somewhere maybe. Okay, all right. Now, since we have put that in, that distance now, okay, that's distance now. If I can just take that one, that vertical distance now is the freehold volume. Okay, is the freehold volume. Okay, so that's the freehold volume. Okay, what's the volume is? I can just simply take that, just put it against there. Okay, just put it against there. So I would say maybe what, 260 perhaps. Okay, maybe 260 to, yeah, about 260. So I'm just going to undo that so it goes back to where it was. I'm going to put the freehold volume is 260. So overhaul volume will simply be the difference between haul volume and the freehold volume. So if I enter that, I will calculate what the overhaul volume is, 520. Okay, now we know that now. So that's how much volume that will be charged for transportation. Okay, now the next thing is to find the average haul distance. Okay, to do that, we need to find the center of this line here, the center of the total volume. Okay, I would just use by examination of the squares, maybe I've got 1, 2, 3, 4, 5, 6, 7, less than 8. So if I go 4, I'll be in between, 4 will be halfway. So I would be somewhere there, I would say. Okay, somewhere there. So if I can just draw a line now, somewhere there, I think that is my average haul. Somewhere 1, 2, 3, somewhere there. I think that would be that would fit nicely. Okay, that would be what the halfway maybe. Okay, between those two. Then that is basically your. Then you draw the line up. Okay, to the top. Okay, I think I should probably bring this down a bit. It should be somewhere there. I think that's more like it, halfway. Okay, so you bring it up there. Okay, the rate of the scale. What's the length? That's the average haul distance there. Okay, the distance between that point and that point, which is, that's what? That's 100, that's 200, so that's 20, 40, 60, 80. I would say 280 meters. Okay, again, do not be too critical. I will just put 280 there. Okay, and we know that freehold distance was is 200 meter. We were told anyway. So overhaul distance will simply be average minus freehold. That gives us 80 meter. Okay, so we now have all the necessary variables, okay, for us to complete with the estimate. Now let's do excavation. So whatever that we excavate, 780 meter, will need to be paid for. So it will cost us 520 per meter cube. So we're going to write 780. So that gives us a total of 4,056. That is for excavation. Then for overhaul, okay, we know that overhaul would be the overhaul volume, which is 520. Okay, 520 there. I'm going to just type there, 520. And we know that the overhaul distance, okay, is 80. So we're going to put 80 there. Oops, excuse me, my bad. Okay, I'm going to put 80 there. So that gives us 282,880. So the total cost is around 290,000 ringgit. Okay, so that will be the cost of transportation of soil, or the movement of soil for about distance about 600 meter. Okay, now you can see from the costing, from the estimate, so it's going to be a rough estimation. I mean, I would quote like 290,000 for the job, or 285 if I'll be a bit more generous. So for that sense, there's no point of us being too pedantic or too critical about when we come up with the numbers. So it's just, I think it's good enough. It's just to scale off the axis, and I think you can do the analysis using an Excel that, like I've just shown. Okay, and I think with that, that'll be the last part, or the last bit of this chapter. And if you got any questions on any of the things that we've discussed, either in this chapter or in previous chapter, okay, feel free to get in touch, either through e-learning, or like some of you have done, you send me messages, and I will try my best to answer. And if you send email, I will try to reply your email. Okay, so thank you very much, and Assalamualaikum and selamat sejahtera.
انضم معنا الآن واشترك بالقناة ليصلك كل جديد. YSAG، معا نحو مستقبل مشرق.